Hey everyone, and welcome to Chem 1411. This chapter is all about the rates of chemical reactions. And so what we're going to find out is whether reactions happen quickly or slowly and what kind of helps determine those speeds of our reactions or the rates of our reactions. And we're going to apply this to many other chapters throughout this entire semester. Well, our first podcast here is going to be the introduction of rates of reaction. So what we're going to do is we're just going to kind of get our feet wet on what the rates of reactions are. And then as we move along from this podcast, we're going to see more and more. We're going to build upon that and see mathematically how we can calculate these rates as well. So let's take a trip down memory lane and think about thermochemistry. If we go all the way back to chapter 6, right, we looked at the energy of reactions, right? And so in this chapter, we talked about whether reactions were exothermic, right, whether we had a negative delta H, or we said that they were endothermic, right, when heat enters the system, and we have a positive delta H associated with that. And so what we want to say then, right, is that a lot of our reactions, right, give off heat to their surroundings. And some of them, we need to put heat into the system. And so what we're going to do then is we're going to talk about whether a reaction is feasible, whether that reaction, right, is going to take place. It must happen at something that we call a reasonable rate, and that is tied into these energy calculations that we did a while back. Well, we're going to talk about these different factors that influence the rate of reactions throughout this entire chapter. One of them is the concentration of our reactants, right? And so notice that we only care about how many of our reactants are present. So what we have that are reacting together, the more and more of those we have, then the more likely they are to come together, and the faster our reaction will take place. Next up says the process by which the reaction takes place. So that's kind of like if you had maybe like a couple of different powders versus those powders that were dissolved in water, that's the process by which our reaction takes place. In aqueous solution, those ions are going to be more likely to interact than maybe a couple of powders would. Then we'll talk about temperature influencing it, this thing that we call a catalyst, right? We might have heard of a catalyst before. We're going to talk a little bit about those. And then reaction mechanism. Reaction mechanism, that's kind of a fancy way of just saying like, all right, what steps does our reaction need to take place in order to end up with our final products? So let's take a look at a general equation here. And this is the general equation that we use for our reaction rates. Here I have dinitrogen pentoxide, or N2O5, and it is decomposing into nitrogen dioxide and some oxygen there. And it asks us a couple of questions that we might want to think about to ourselves. All right, so we've got our N2O5. Notice that every time one of them decomposes, right, we're going to produce 2 nitrogen dioxides and a half of an oxygen. And so there's a relationship, right, between not only like that, but like the concentrations. So if I started with only say some dinitrogen pentoxide, all right, and that's going to be shown here. Let's say that I started with 0.16 molar dinitrogen pentoxide. And then, right, after some amount of time, say 2 minutes, we go down, and we're now at this point, we have lost, right, 0.08 moles per liter of our N2O5. So the concentration of it has decreased. Well, at the same time as that's gone down by 0.08, then notice that the NO2 has increased by twice that amount, right? Because of our molar ratio there in our balanced chemical equation. So it has actually gone up to 0.16 moles per liter. And then the oxygen is also going up because it's being produced, and so it's going up by, all right, well, if the N2O5 went down by 0.06, then the oxygen is going up by half of that, or 0.04, so it's sitting right there. Right? And so there's a relationship between those. And so sometimes we'll see that the rates are related to the change in concentrations divided by the change in the time as well. And we also then plug in the coefficients on the bottom there to get each one of the rates to be the exact same. So notice that the rate of our N2O5 is decreasing, that's why we have a minus there, by some amount. Well, then the rate of our NO2 is increasing. There was an implied positive sign out back there. It's increasing, right? The concentration is increasing by twice the amount. So we're going to divide by 2 so that those rates are going to be the same value overall. That's what we're talking about with our rate of reaction. So we can write out the rates of our reactions by saying that, okay, the products, or sorry, the reactants are going down, so we have negatives out in front, and the products are being produced, and so they would have implied positives out in front of them by the change in their concentrations. And then we divide each one of them by their coefficients times the change in time for each one. All right, and so we can do that for any reaction, and then I've shown that there for having nitrogen and hydrogen combining to form ammonia. Right? But we can do that for any one, and you may see these sorts of things on a homework assignment or something. I'm going to steer clear of these on any exams or something because I don't feel like they tell us a lot of information when we're talking about the rates of our reaction. When we get into actually working out the mathematics on these, then that makes a lot more sense than just seeing these generic forms. But this generic equation at the top, all right, that we see here, okay, we're going to see that a lot throughout our semester, so that's why I leave this slide in, right? And so that's just saying that, right, each one of our lowercase letters are different coefficients, right? So A of A means there's some number of some compound A, plus B of B, right? So there's some number, so there's some coefficient, lowercase b, of some, all right, element or compound B, and so on. Right, so just get used to seeing that general equation, because that's going to hop up for several different chapters when we're talking about things. Well, as we stated earlier, right, our reaction rate is related to the concentration of our reactants. Okay, and so my example here on this slide is hydrogen peroxide. Right, hydrogen peroxide is the H2O2 there. And so we've probably all seen some hydrogen peroxide at some point in our lives. And we've probably only dealt with some pretty dilute hydrogen peroxide. Right? But hydrogen peroxide will decompose and produce water and oxygen. And those are both in the gas phase. So if you say were to pour it onto like a cut on your skin, which they tell us not to do anymore, but they used to think that was a good way to clean it out. Right, when you pour it on there, you'll notice that it'll bubble on that cut, and those are those gases. So that is when we're seeing the hydrogen peroxide decompose. All right, what we see from our drugstore hydrogen peroxide is this probably around like 1 molar, and the reaction itself doesn't take place very fast, right? You can have a bottle of hydrogen peroxide in your house, and it's very stable for a long period of time. Whereas if we had pure hydrogen peroxide, that decomposition is very fast, and it's explosive because, right, we're going from a liquid to the gas phase, and gases take up a heck of a lot more space than a liquid does, and so they're going to explode out as they expand, right? And so the higher that concentration is, the faster that reaction takes place. One way that we can observe our rate measurements is by doing something that we can physically see. So with our hydrogen peroxide, we could see that it was decomposing and turning into a gas because we'd see the liquid disappearing. Another way that we could do that is we can see a color change. All right, and so again, we've got our N2O5 decomposing there. That was our general equation that we used a while back. And so notice that it could go from, when it's the N2O5, right, as it decomposes, we actually see it change colors. It goes from a brown color until a much lighter brown color. It's still a brown color, but it's much lighter. In order to see this a little bit better, on the bottom I have something that is not that chemical reaction. What it is we have some blue dye in a beaker, and we're going to add some bleach to it and see that blue dye then get bleached out. And so we see it go from that dark blue to a lighter blue to almost a colorless solution as time goes by. And so we can visually see that, and we can also hook that up to instrumentation that can give us some calculations as well, right? But that's one way that we can see that some sort of a reaction is taking place, is by some observable change. Well, one way that we can, explain the fact that the higher the concentration of our reactants, the faster the rate of our reaction occurs, is by thinking about the rate with a collision model. So if we think about this, this does not work for our decomposition reactions, but it does work for reactions where we say had like A plus B maybe forming C, right? A combination reaction, right? So this is a reaction where we have like a couple different particles actually colliding together. Well, if we think about it, here I've got a couple different pictures, but on the bottom, right, like let's just say that I had two different layers. Well, notice on that top layer, there's a few particles up there. On the bottom layer, there's a heck of a lot more particles. So if we're thinking about it, right, if we have a heck of a lot more particles, they are much more likely to hit each other. And if they're more likely to collide, right, and we need a collision for a reaction to take place, well, the more often they collide, the more often that our reaction happens, thus the rate of our reaction will increase. So a way that we can look at, right, an increase in the concentration is in this picture here, this figure. All right, so I used to say, okay, here we've got some red balls and some blue balls, but that didn't go over so well in class. So, well, it probably went over too well in class. So we're going to call these red spheres and blue spheres. So notice on my left panel, I have 10 blue spheres and 1 red sphere. And notice that, right, it's going to collide, that red sphere, if I shoot it in there, it's going to collide with 2 of the blue spheres every second. All right, well, notice that when we double the number of blue spheres on that right panel, so we have now doubled them to 20 blue spheres. Notice that if I have the 1 red sphere still in there, it is going to, right, come in and collide with 1, 2, 3, 4 of those blue spheres. So when I doubled one of my reactants, I am doubling the number of collisions, which would also then find out to double the reaction rate that we would have. All right, so that's the end of podcast number 1. Once we come back for podcast 2, we're going to actually start looking at these rates and their mathematical equations.